So let's go on to talk about the demos, described on the back page of the second page of the PDF that I'm sending you. We had ourselves a demo with a ladder that was on the verge of slipping, and when we moved a weight up, we could make it slip when the torque of the weight got bigger and bigger. We compared that to putting a rug on the wall, and we found that it slipped almost just as soon. The friction of the rug was negligible, and the reason is that the normal force from the wall is balanced by the friction force, which is not very big, from the floor. But then the friction force is thus just that much smaller, mu times that n, so that the friction force is not very big. We came back to look at this spool where we found that the cute result that when we pulled on it at kind of a small angle with the horizontal, it would go to the right. If we pulled on it at a bigger angle, it would roll to the left. But if we pulled at it just at a critical angle, where the line along the rope, tangent to that inner spool, goes through the contact point, there'd be zero torque then due to the rope, that it wouldn't roll either way. If we pulled hard enough, it kind of lift. We looked at a rod pivoting around an end, and we found the neat thing was that when we let it go with an eraser on the end, the eraser couldn't keep up on the end, but it could keep up in the middle. And that was just the well-known result that we spent a lot of time on, that the angular acceleration is such that the acceleration of the end is bigger than free falling. But of course, it gets less and less as we get closer to the pivot. When we spun a bicycle wheel with handles on it, put it at an angle, we spun it clockwise, or rather counterclockwise to start with, then it would precess counterclockwise. On the other hand, if we spun it clockwise, it would precess clockwise. The reason is the torque to the gravity is the same in both. Here, it would tend to, with the angular momentum pointing that way, tend to push the top around. Here, with the angular momentum pointing down, it would tend to push the bottom, and so the top came toward us instead of away from us, and would spin and precess around clockwise. All we did on the next demo was to just simulate a river with a piece of paper, start a little motor car at some angle, and because of the motion of the paper, the net velocity relative to us looking at it was bigger. And our triangle that we would analyze this with is now a scalene triangle instead of one with the right angles, and that's something that we were doing calculations with. A favorite demo of mine is taking coffee filters. They're so light that the drag force immediately cancels the drag force is proportional to speed, but the speed immediately gets big enough to cancel the light weight so that it then falls without acceleration at terminal velocity. And we could compare that to a baseball with negligible air drag and see how much faster the baseball fell. To check this model, we took 2 coffee filters, thus twice the mass. For them to be canceled by the drag, they had to have twice the velocity. But comparing with this guy, now when we look at this, sure enough, this thing was falling faster than this, even though they both were going at constant speed. And we could check that by starting this guy up at twice the height, and they both would hit the table at the same time. In the Demomania, we ended up with with this quickie where if we have a tube, we couldn't see what the mass was inside of it. We knew they weighed the same. If one had the mass in the middle and the other had the masses at the top hidden from us, we found this was so much harder with the same torque, same hand grip in the middle to twist compared with this guy, because the moments of inertia were so different. Moment of inertia was a key in the next demo. The surprising thing is the weight at the top of a rod will make this thing fall slower than the weight at the bottom. They're both pivoting at the bottom here. That's because this has much bigger moment of inertia than this, much bigger inertia. Torque is bigger, but moment of inertia is quadratically bigger. Then we had our favorite little blue crayon, where if we supported it, say 1/4 of the way in at the end here, this support force is twice this, and therefore the maximum friction that this can have is twice this. And so we end up, when we push our hands together, this one easily slides in where this one doesn't hardly move at all initially, just because of the difference in the maximum friction static force. We went back to something that we'd already talked about. If we took a balloon, threw it up, it stopped more quickly than it took to float down. And that's very easily understood because the drag force and gravity work together to try to stop it here, but then they tend to cancel each other when it's floating down. And as a result, it doesn't come down as fast as it stopped going up. We took a fan with a mock-up of a sailboat, a car on a real nice frictionless track, take the sail on it to be perpendicular to the fan, and you could see how much faster this was than when we're at an angle, for the two reasons, fewer molecules hitting, and also the net force was at an angle then off the reflecting of the molecules off the sail. But if we had the track perpendicular to the fan, we could actually keep accelerating this thing. And if this angle were small enough, we could go faster than these guys. We could go faster than the speed of the wind eventually. Then we revisited just letting a marble go across a rotating platform. We know as a part of the Coriolis effect that this would be deflected to the right. If we had a motorized car, it would go straight. It must be that the force due to friction was keeping it and fighting the force due to the Coriolis effect. And that meant, of course, the Coriolis effect was kind of trying to push this thing counterclockwise, and so this guy was canceling it and pushing clockwise. Finally, our greatest astro rocket demo, we had an amplifying effect. If we had 4 balls falling down and at some speed, when they bounced off, the top guy shot off to the ceiling. There's a huge amplifying effect. And what is important for you to think about is when we just had this guy, every one of these guys, think of it being much lighter than the one below it. And then we could play the game where, remember, we saw that when we had a small guy, and a big guy hitting the floor, this guy would shoot back up at 3v, remember, by doing our relative velocity stuff. And it was easy to visualize it in the rest frame of each of the heavier ball, and then add back in its velocity to get what we see. So the first guy gives 3v, check it. The next guy gives 7v, and the next guy gives 15v. Check that. See if you come up with all of that. By the way, we had kind of a special post here that stopped these three from leaving the post so that only the top one was free to get finally off, which was why it shot off by itself.